We will have the first form of a tree, that is binary trees. What exactly the definition of a binary tree would be? I'll give you a formal definition for a binary tree. You can note down the definition, then we'll discuss what is the binary tree is. A binary tree T, say if I am denoting it with some symbol T, I'll say a binary tree T can be empty. A binary tree can be empty, comma, if it is not empty, contains a root element, with each node in a tree, containing at most two child nodes. There are certain things to be discussed in this particular definition. First and most important thing is, while giving the definition of a tree, I said that a tree cannot be empty, isn't it? But I am saying here that a binary tree can be empty. That means that you cannot define a binary tree with respect to a tree, because it has its own properties. So we say a binary tree is a tree. No, the definition won't be like that. A binary tree is a tree. No, a binary tree can be empty. Say T, I can have an empty binary tree. If it is not empty, it contains a root element. Say a root element A is there, with every node or each node in a tree containing at most two child nodes, meaning for this at most less than or equals to 2. Less than or equals to 2 means I can have 0 child node, 1 child node, or 2 child nodes I can have. Its definition says that each in this particular structure can have 0, 1 or 2 child nodes. Then only it can be a binary tree. Otherwise, if it is not satisfying this property, then you say this tree is not a binary tree. Okay. Then what are the differences between a tree and a binary tree? One difference we have already came across in the definition part itself. What is the definition? Says that a binary tree can be empty, whereas a tree cannot be empty. That is the first difference you can have it. Tree over here, binary tree over here. What is the first difference? A tree cannot be empty. Whereas a binary tree can be empty. It's not always empty, can be empty. When I am saying can be empty, cannot be empty also. So, maybe, may not be. There is no number of child nodes restricted over here. So that means that no restriction on number of child nodes. But there is a restriction over here. What is that restriction says? At most 2 child nodes. There are 2 points what you need to consider regarding tree and binary tree. A tree cannot be empty, whereas a binary tree can be empty. And there is no restriction on number of child nodes you can have. As we have seen, we have 3 child nodes, even we can have 4 child nodes. More than that also we can have the number of child nodes. So there is no restriction as such on the number of nodes what it should contain. Whereas here there is a restriction in the definition itself. They says that it should be at most 2 child nodes, which says that it should be either 0 or 1 or 2. Can make a note of this differences, and at most meaning over here is this one. I'll draw some of the tree structures over here. You identify how many among these are binary trees actually and how many are not binary trees. Let us start with the first one here. Some of the structures I have drawn over here. I'll label this one, say number it 1, 2, 3, 4, 5, 6, 7, 8, 9. Among these 9 structures, whatever is there in front of you, how many are binary trees and how many are not binary trees? Let us start with the first one. First one is a binary tree. Yes, it is a binary tree. Binary tree with only one node, that is root node, may not have any child node, so it may be 0 child node. One child node possible. Yes, one child node possible with root node. Then you can have 2 child nodes possible, not having any child node to its left, can have right child node. Only one child, again one child, can have 2 childs at most maximum. Yes, you can have. With the definition of binary tree, what it says? A binary tree can be empty. So nothing is there over here. Instead of writing dash over here, even I can say, or I can specify this particular one by saying null. Both are same. Nothing is there in this particular structure, null value. Empty binary tree, you call this particular one. Then what are these structures are? Is it going to be a binary tree? Same as a structure like this, or there is a difference? Let us see. here one node called as root node is there, here one node is there, but there is a significant difference between these two nodes. This is labeled node, this is unlabeled node. That means we have not put the value in that one, just a node structure we have drawn. Not value is designated for that one. So you call that one as a unlabeled node. What is this one is then? Unlabeled tree. This one is also unlabeled tree with only single node. That's why I am saying this one is unlabeled node. This one is also unlabeled tree. Unlabeled tree. This one is also unlabeled tree. So here these three structures what we are seeing all are unlabeled. Whereas the remaining all are labeled one. This is also labeled, this is also labeled, labeled with some name. This is something referred to as empty binary tree. This part. All are unlabeled binary trees. Remaining all, this part or the remaining part, all comes under your labeled one. Labeled binary trees I'll call. Now, see the differences. Among labeled also there is a difference. What is that? Is there any difference between 2 and 3? Yes, there is a difference among 2 and 3. What is that one? It says that there is no right child for root node. There is no left child at all exist for root node. So what type of tree this one is going to be? This one is now said to be a left skewed binary tree. Left skewed binary tree, whereas this one is referred as a right skewed binary tree. Then is this one is skewed one? No, nothing is there in its left, nothing is there in its right. Then coming into this category and this category, what exactly this category of tree is said to be? I have some nodes which are complete within it. There are appropriately at each level sufficient number of nodes are there. At this particular, you see at this particular tree also the same thing. The level structure of A having exactly one node, it is having one node. Exactly two nodes, two nodes. Four nodes are full. That means that this form of trees are something referred to be as full binary trees, or they are also called as, in this particular scenario, they are also complete binary trees. Full as well as complete I am saying. This also applies the same. This is also full or complete. Then what is the basic difference between full and complete binary trees? Coming into this particular part, what type of tree this one is? Again the same. It is again full or complete. Full or complete, left skewed, right skewed, full or complete, empty binary tree, all are unlabeled, can repeat the same thing. Among unlabeled, this one is full or complete. Among unlabeled, left skewed one. Among unlabeled, not right skewed, you can say. This one is not a right skewed one. You can't label this one as a right skewed. Why? Should have only right nodes. There should not be any left node to be exist within the tree until you reach the last node. there is a left node exist over here. So I can't say this one is not a right skewed one. Yes, this is a left skewed one, I can say, fine. True. Left skewed is true. Right skewed is false. Coming it to, I said full as well as it is complete. Keep that particular thing in mind. When I am saying it is full and also it is complete, we will see the difference now. Now when I say left skewed, what would be some of the other left skewed binary trees can be? Can I say A with B with some other, say, E node over here is also left skewed? Yes. Left node only. There is no right node in the tree exist. Perfectly a left skewed binary tree. Same way I can have it for this one as only right childs exist. Only right child. Whatever the level you go into, 1, 2, 3, 4 level, 1, 2, 3 height, whatever we are traversing it, it is again a right skewed binary tree. Coming it to the difference to understand between full and complete now. Let us see it over here. I'll say A, B. Is this one is a full binary tree? No, not a full binary tree. Reason is a full binary tree should have all the number of nodes within that particular level. This level, if I just put it something like one node only and ask, is this one is forming a full binary tree? Then your answer is yes, it is a full binary tree. If I add one node to its left and I'll ask you whether this one is forming a full binary tree? No, it is not forming a full binary tree. Then I'll have one more node structure over here by saying that I'll add a node over here. Is this one forming a full binary tree? No, this one is also not forming a full binary tree. Then if I have both the nodes to be given as say B as well as C, then only this one is forming a full binary tree. Neither among this one is full binary tree. But coming it to one more type what we have among this full and complete is, let us concentrate on complete. Among these two, is there any one which is, I can say, is a complete binary tree? Yes, this one is a complete binary tree, whereas this one is not a complete binary tree. Then what would be the difference? The difference is you derive a complete binary tree from a full binary tree such that if you start deleting the node from the last node in the tree till we reach the root node, there should not be any empty memory location between two nodes. What is that? I'll repeat once again. You derive a complete binary tree from the existing full binary tree. Say for example, this is existing full binary tree. If I assume, if I start deleting the node, say which node will be the last node in the tree currently, you start reading it something like this. At level 1, you give preference or number 1. Then you will not read C first, you will read B first. So you give number as 2, then you give number as 3. So for my tree, this particular tree, C is the last node in the tree. So what I said is, I'll derive a complete binary tree from a full binary tree such that if I start deleting the node from the last position till I reach the root node, then if there is no empty memory location in between the two nodes, then I'll call that tree as a complete binary tree. Example, one more we will take over here. This one, C we have deleted from here, we got this. Yes, it is a complete binary tree. But here in between in the sense, let us label this one as C only, say for example. Why? Because here A, B, C are there. I have deleted B before deleting C. then there is empty memory location in between A and C. So this cannot be a complete binary tree. Take another full binary tree, this particular one. So I'll now take this full binary tree as A, then B, then C, then D, E, F and G. Obviously it is a full binary tree. What is a full binary tree? We will see with respect to the formula also. We will define it formally what is a full binary tree is. Right now for every node I have exactly the number of nodes are filled up. There is no empty memory location over here. So I'll say this one is a full binary tree. Fine. Once it is a full binary tree, now if I start deleting a node from the last position in the tree, what is the last position in the tree is it's node G. I will be labeling the node something like this: 1, 2, 3, then 4, then 5, then 6, then 7. Seventh node, that is the last node in the tree, is G. So if I delete from this particular tree one node, say G is removed. Okay, before deleting it, it is full as well as it is complete. So I can say all full binary trees are complete binary trees. True or false? Yes, true. All complete binary trees are full binary trees. No, not satisfied, because here one example is this one. This one is a complete binary tree, true, but it is not a full binary tree. This one is a complete binary tree as well as full binary tree. So satisfied for some trees, satisfies for not some of the trees basically. So all full binary trees are complete binary trees by default, whereas on the other hand reverse is not true. Coming it to, from this particular node tree, if I start deleting say G, if I have removed, will it be a complete binary tree? Yes, it remains a complete binary tree, because we have seen that last node is deleted, no empty memory location between any of the nodes existing in the tree. If I start again deleting 6, again it remains binary tree, is a complete binary tree only. So if I derive it from here, I can have multiple complete binary trees like A, then followed by B, then followed by C, then D, E, F is one of the complete binary tree. Then is this structure whatever we are having, then one more node if I delete, A, B, C, then D, then E, I am saying. Yes, when it is derived from this one, yes, it is again a complete binary tree. So this one is a complete one, this one is also a complete one. If I now delete D, as a result, if I delete D, what would be the resultant tree now? You will get it is A, followed by B, followed by C, then nothing is there into the left, then there is a node into E existing. This is derived from here. So you are deriving it from here to here, from here to here, from here to here. Full as well as complete, these two are. Yes, true it is. Full as well as complete. Coming into this one, not full. Obviously it is not full because last node is missing. It's not full, leave it of that one. Is it complete? Yes, it is complete. Coming into this particular part, is it complete? No, it's not complete because there is empty memory location shown with dot over here is missing. So I'll say it is not a complete binary tree. Not a complete binary tree. You can note down one by one. First of all, you can copy down the contents from the board. It is something like this. You draw the structures from this here part and you can label the names whatever is there. Example skewed trees, what I have taken it over here is example 2, example 1 more example, you can take it. Right is skewed, there are 2 examples. Full and complete, there are three examples here. This one is also full and complete. Then coming into the last concept, among full and complete, what exactly the difference is. Can note down this part. Let me just recollect the things, whatever we have done before going for the next concept is, first of all, we have defined a binary tree. Then we have seen how many among these are binary trees. I have listed some over here, where all are binary trees here. This is one form of binary tree, something called as full or complete. You say that it is full or complete binary tree. What is the difference between this full and complete binary tree and this full and complete binary tree? This is a full or complete binary tree of height 0. This is full or complete binary tree of height 1. Because we say that leaves are always referred with respect to nodes. Height is always referred with respect to edge. Then we have height of this particular one. This is also full or complete, but it is of height 2 now. So the difference over here is height 0, height 1, height 2, different binary or full or complete binary trees. First you make a note of this one. Level of a tree is referred by the nodes and height is referred by edges. Therefore, full binary tree of height 0, full binary tree with height 1, full binary tree with height 2. Coming into left, another form of binary tree, left skewed binary tree. All are left child exist, right skewed binary tree, only right child exist. Combination of this one not possible. Say here, one right child, one left child, not a right skewed. Even it is not a left skewed also. It is just a binary tree, you can say. So it's not a special form. One is special form is over here, null, nothing is there. You call this one as a empty binary tree. Empty binary tree. Then these are some special forms again. Not put any values into the node, not labeled one, just to say unlabeled binary trees. All remaining other are labeled binary trees. Among labeled we can have skewed, left skewed, right skewed, then complete, full, all. Then what is the difference we have seen among full and complete is, complete binary tree is derived from full binary tree by removing the nodes from the last position such that we should not have any empty memory location. You can make a note of these definitions. First of all, a left skewed binary tree. A binary tree with only left childs. A binary tree with only left child exists is a left skewed binary tree. Similarly, a binary tree which contains only right childs is a right skewed binary tree. Is a right skewed binary tree. Now I have given the height for full binary tree 0, height 1, height 2. We will define now full binary tree with respect to height. Okay. How many number of nodes a full binary tree should contain? How many number of nodes a full binary tree should contain? With height 0, one node is there. With height 1, there are 3 nodes are there. With height 2, there are 7 nodes are there here. Nodes are 7. Nodes are 3 here. Number of nodes in a tree. And here number of nodes in a tree are 1. So how do you define a full binary tree with respect to the given height? H. When H starts from 0. When H is starting from 0. So when I say 0, it is going to have 1. When it is going to be 1, it should be 3. How you can achieve that one? Is, I'll have one formula, say 2 to the power H plus 1 minus 1. Then if I substitute H value here as 0, H is equals to 0 if I substitute, then I'll get the number of nodes. This is n number of nodes. What I'll get it n as, I'll put H somewhat larger like this. Then n, 2 to the power 0 plus 1 is 2 minus 1. So it's going to be 2 to the power 1 minus 1. So you will get it as 1. So 1 node. Similarly, if I say height is equals to 1, I'll substitute and get it as 2 to the power 1 plus 1 is 2 minus 1. So it's going to give me the number of nodes are 3. Similarly, I'll substitute height is equals to 2. Then I'll get the number of nodes as 2 to the power 2 plus 1. That is 3 minus 1. So it's going to give me 7. It's satisfying this particular condition. Whenever height is 0, we have number of nodes as 1. Yes, it's satisfying here. When I say height is equals to 1, number of nodes are 3. Yes, it is satisfying here. When height is equals to 2, we have the number of nodes as 7. Yes, it satisfies for all. So now you can define a full binary tree as follows. Given n number of nodes, with height h, a full binary tree contains exactly n is equals to 2 to the power h plus 1 minus 1. Here formula, n is equals to 2 to the power h plus 1 minus 1 number of nodes, contains exactly 2 to the power h plus 1 minus 1 number of nodes. Example, 3 examples you can take. Height 0, you will get 1. This is the example. Height 1, number of nodes 3. This is the example. Height is equals to 2, number of nodes 7. That is the last example. You can note down this definition. I'll give you the definition for complete binary tree as well. Now, note down the definition for complete binary tree. A complete binary tree is derived from full binary tree. A complete binary tree is derived from full binary tree such that if the nodes are deleted, from the last position to the root node, that is first position. From last position to the root node, that is first position, then there should not be any empty memory location. In between the two nodes. There should not be any empty memory location in between the two nodes of the resultant tree. Then it is called as a complete binary tree. And the last point is, all full binary trees are complete binary trees. All full binary trees are complete binary trees. Whereas reverse is not true. This is regarding your basics of the types of trees what we have. Next we will continue with the topic.